David Smith here with one more flipped classroom math lesson. 3 tips. First, you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to catch up with your notes or jot down some questions. Third, you can turn on the captions and read my words on the screen. So today's lesson, we're going to cover the area problem. Along with the tangent line problem, these 2 problems are kind of central to the development of calculus and are a core of our pre-calculus unit. So let's get started. So here's an interesting question. I have a graph of f of x equals x squared. This is the mother parabola. All parabolas are related to this one. And here's a question that I'm going to ask. What is the area under the curve from x equals 1 to x equals 2? So I've shaded in that area there, and we're going to ask the question, what is that area? How might we calculate it? Okay, so now we're going to do an approximate calculation of that area. So what I've done is I've taken this graph and blown it up. We're just showing the positive arm of our y equals x squared parabola. And what I've done is I've divided the interval from 1 to 2 into 4 parts. And I've made 4 little rectangles. We're going to calculate the area of those rectangles as an approximation of the area under the curve of this section of our parabola. So the first rectangle is 1 high and 1 1/4 wide. The next one is 1 1/2, is another quarter wide. The third one is a quarter wide, and the fourth one is a quarter wide. So let's take a look at how this looks. The first rectangle is 1 high. So it's going to be 1 times 0.25. Okay, so that's our first piece. Then we're going to add, the next one is going to be also a quarter, but it's going to be, the height is f of 1.25 times 0.25, right? Because the height is when you put the x coordinate, which is 1.25, into the function to get the y coordinate, which is the height of that rectangle. And then we're going to add 2 more. We're going to add f of 1.5 times 0.25 plus f of 1.75 times 0.25. So those are the 4 little quantities that are going to give us our areas of these 4 rectangles. So let's factor a little bit here because I've got a 0.25 in each of these terms. So now I can factor that out, 0.25 times 1 plus f of 1.25 plus f of 1.5 plus f of 1.75. So now I can calculate that out with my calculator. 1 plus 1.25 squared plus 1.5 squared plus 1.75 squared equals times 0.25, and here's what I get, 1.96875. So the area of this is 1.96875. Now, how accurate do you think that is? Perhaps not very, because check this out. We left out all these areas. These are also areas under the curve, but they're not captured by our rectangle. So what I want you to do is pause the video and think about what you might do with this method to get a better approximation. Okay, if you thought, let's just increase the number of rectangles, you are right. And that's all we need to do. So check this out. I'm going to do the calculation for 10 rectangles. Okay, so if I have 10 rectangles, then each increment along the bottom is just going to be 1/10 or 0.1, 0.1. And that's going to be times f of 1 plus f of 1.1 plus f of 1.2 plus, I'm not going to write them all out, plus f of 1.9. Okay? So I'm doing the same calculation I did here, but now I'm doing, instead of a quarter wide rectangles, I'm doing a 1/10 wide. And then instead of increasing by a quarter every time, I'm increasing by a 1/10 every time. And so now I can put that in my calculator, and let's see what we get. So when we do that calculation, here's what we get. We get 2.185. Okay, so our area's gone up, which is what we would expect. We've gone up from 1.9 something to or approximately 2.2. So again, we're not all the way there. So here's what we would do. We're not going to do that because the math gets pretty complicated. It's not essential for doing the homework and the lessons that are coming. What we would do is actually pause this for a minute and think about it. What would you do to find the exact area? Okay, if you thought, take the limit as the number of rectangles goes to infinity, you're exactly right. So we would take the limit of an expression like this and run the number of rectangles to infinity, run this number to getting very, very, very tiny, and you would actually be able to calculate the actual area. However, there's a quick way to do this, and this involves integrals. So we just finished up a couple lessons on doing integrals, so now we're going to use them to solve this area problem. Okay, so here's where the integral comes in. Here's our problem. Find the area under f of x equals x squared. That's the graph we just looked at from the point 1, 1 to the point 2, 4. So that's what we did, and we approximated that area with 10 rectangles, and we got 2.185. That was with 10 rectangles. So what do you think is going to happen when we get the exact calculation? Pause the video and just tell me what's going to happen to that number. Okay, if you said it's going to increase, you're right. It has to increase because we're going to include all those little bits that the rectangles did not capture. So let's do that. The first step, take the definite integral of the function. So the definite integral means we don't worry about the plus c constant. Okay, so let's do that calculation. Here's f of x. It equals x squared. So to get f prime of x, we do the following. F prime of x is going to equal 1 over 2 plus 1x to the 2 plus 1. This ends up being 1 over 3 x to the third, which we simplify by just going x to the third over 3. Okay, so now what we do is we use the integral of f of x, this function that we just derived, to subtract the lower boundary from the upper boundary. So here's some notation for how to express that. We're going to use our integral sign, and here's our boundaries, x equals 1 to x equals 2, and then f of x is just x squared dx. So this is saying, let's take the integral of f of x from 1 to 2. Now what does that mean? We're going to do this. We're going to use the integral, so we're going to do f prime of 2 minus f prime of 1. This is the upper boundary, that's the lower boundary. Okay, so now we're going to do a little bit of plugging and chugging. What's f prime of 2? Here's f prime, so f prime of 2, we put 2 in for x, so that's going to be 2 cubed over 3, and then f prime of 1 is just 1 cubed over 3. We're going to get 8 over 3 minus 1 over 3, so our answer is 7 over 3, and that's going to be 2.3 repeating. It's pretty much that straightforward. Now check this out. When we approximated with 10 rectangles, we got 2.185. Now when we get the exact area, it's just 2.3. So a small increase, but an increase nonetheless. So now I'm going to give you one to try. Try it from x equals 2 to x equals 3. And that is the point 2, 4 to the point 3, 9. So go ahead and pause the video and run this calculation on that function to find the area under the curve from the point 2, 4 to the point 3, 9. Pause the video and give that a shot. Okay, so let's see what we get. I'm going to write this as an integral. This is from 2 to 3 of x squared dx. That's going to equal f prime of 3 minus f prime of 2. So now we just do our plug and chug. We're going to get 3 cubed over 3 minus 2 cubed over 3. So this is going to be 27 over 3 minus 8 over 3, which is going to give us 19 over 3, which equals 6.3 repeating. Now that makes sense, because as the parabola is going higher and higher, those individual rectangles are getting taller and taller and taller, so our area is going to get bigger and bigger and bigger. So there you have it. Okay, let's do a more complex one and run that all the way through. So here's the question. find the area under f of x equals 5x squared from the point 220 to the point 125. So let's do those steps. First step is to find the integral of this function. So if we have f of x equals 5x squared, then f prime of x is going to be 1 over 2 plus 1 times 5x to the 2 plus 1. Okay? So that's going to give us 5 over 3 to the x to the third. So I'm going to simplify that as just 5x to the third over 3. So that's our f prime of x. Second step is to run our derivative, or our integral. So now we're going from the point 2 to 5 of 5x squared dx. That's going to be f prime of f prime of 5. You do the second one, the upper boundary, minus the lower boundary, which is f prime of 2. Okay, so I recommend doing this step just so you have that information down so you don't mess up on the plug-in step, which is now what we're going to do. So f prime of 5 is going to be 5 times 5 to the third over 3 minus 5 times, let's put parentheses around 2 to the third, that's 5 to the third, and that's over 3. Okay? Now, 5 to the third is 125, times 5 is 625 over 3, that's a 3 there. 2 to the third is 8, times 5 is 40, minus 40 over 3. That's going to be 585 over 3, which is going to give us 195. Now this makes sense. Remember, our last one we just used x squared. Now we're multiplying it by 5 to get the y value. So that function is increasing way more quickly. We're running it also from 2 to 5. So we've got 3 increments on the x. So our area under that curve is getting bigger and bigger. Okay, let's do one with a root. Okay, so here we go. Find the area under f of x equals the square root of x from the point 1, 1 to the point 4, 2. Okay, so pause the video. Remember how you express root x as a power and see how far you can get. Okay? Okay, here's our first step. If f of x equals root x, I'm going to simplify that to x to the 1/2 power. Remember, the square root is the 1/2 power. So here's our function. We've expressed it as a power, so we can use the power rule for integrals. So now we're going to get f prime of x is going to be 1 over 1/2 plus 1 x to the 1/2 plus 1. So that's using my integral rule. Let's simplify this out. This is 1 over 3/2 times x to the 3/2. And now we have to play around with our fractions and our exponents to get this into a nice form. So 1 over 3/2 is the same as multiplying by 2/3. So I have 2/3 times, let's use a dot. Now the 3/2 power is the square root of x to the third. Okay, so remember your exponent rules. So now this is going to end up being, to be simple, 2 times x to the third over 3. So that is our f prime of x. So if you stopped, if you couldn't work it through to this point, now that you've got this point, again, pause the video and find out the area under the curve. Do step 2. Okay, see if you can get that. Okay, so let's write our integral. Here we go. We're going from the point 1 to 4. So it's from 1 to 4 of root x dx. And that's going to be equal to f prime of 4 minus f prime of 1. So here's our integrated function right there. Now we're going to do our plug-in step. We're going to plug in 4 in my function. So it's going to be 2 times root 4 to the third over 3 minus 2 times root 1 to the third over 3. Now if you followed along with me, pause the video and see if you can analyze that to get her all done. Okay, so 4 to the third is 64. So we have 2 times root 64 over 3 minus, now root 1 cubed is 1 and root 1 is 1. So this is just going to be 2 over 3. Now you know what root 64 is. That's 8. So we have 16 over 3 minus 2 over 3, which gives us 14 over 3. And 14 over 3 is just 4.6 repeating. So there you have it. Now, get ready for the homework. You're going to have functions with squares. You're going to have functions with complicated roots. You're going to need to use all your exponent rules, carefully integrate your functions, and then be careful about plugging in and doing your calculations. Now that you've watched the video, take a moment to jot down some notes, some questions, or a quick summary of the content. You can also re-watch the portions of the video that were a little bit challenging. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.